Hello, my name is Vladyslav Shlianin and I am software engineering student at Faculty of Informatics and Computer Science at Igor Sikorsky Kyiv Polytechnic Institute. Today I am presenting my paper Link Prediction Method in Graph Objects by Auto-Encoding in Graph Neural Networks. So, the basis of this research is a link prediction task, which can be defined as predicting whether two given nodes in a graph may or may not have a link between each other. It is a pretty common task for a graph structure data. Most frequently it is used in the context of social networks or recommender systems. Traditionally it is based on heuristic methods such as CATS index and others. But the problem is that it is not applicable for all datasets. In some cases, nodes may have completely different properties and still have a link. Also, it is worth noting that link prediction based on graph autoencoders is underrepresented in existing researches. The main aim is to increase link prediction accuracy in graph neural networks, utilizing graph autoencoder architecture. To reach this aim, following tasks were planned: preparing datasets suitable for GNN, applying GNN with graph autoencoders and variation graph autoencoder architecture, comparing graph autoencoder and variation graph autoencoder performance on link prediction task, and exploring GNN performance differences based on graph convolutional network configuration within model. For the purpose of this research, customized dataset was constructed, which consists of legal acts adopted by Ukrainian parliament and Ukrainian government. It contains more than 68,000 acts and more than 89,000 links between them. This data can be represented as a directed graph, in which nodes are acts and edges of this graph are links between said legal acts. For the purpose of this research, 4 different models were created and all the models implement graph autoencoder architecture. This architecture consists of a decoder and encoder. The encoder takes data from input and transforms it into a lower dimensional embedding Z. Then the decoder takes this lower dimensional embedding and reconstructs the original input. Usually, graph convolutional networks are used as an encoder and dot product is used as a decoder. Also, a portion of models implement variational graph autoencoder architecture. In variational graph autoencoder based model, encoders output mean and variance vectors, which are converted to Z embeddings, and encoders of regular graph autoencoder models output this embedding directly. So here on this slide you can see 2 models which are implementing graph autoencoder architecture. The first model has 2 graph convolutional networks and the ReLU function. The second one has only a single graph convolutional network, which is why it is called a linear model, linear GCN, and this one is just GCN model. And on this slide you can see 2 models which are implementing variational graph autoencoder architecture. This one has 2 graph convolutional networks and the ReLU function, and this one has a single graph convolutional networks. And both of these models output mean and variance vectors on the encoder parts, and these vectors are transformed into a Z embedding. And of course this model is called VLGCN model because it is variational graph autoencoder model and it is linear since having a single graph convolutional network, and this is a VGCN model. And each model's training process was performed 10 times to calculate mean performance and standard deviation. Each training iteration was done with a randomly generated seed and all models were reset each time. And here on this slide you can see the results. As you can see, GCN model, the one with 2 graph convolutional networks, and the model which is implementing graph autoencoder architecture is the most efficient. However, the performance differences between all the models is not that significant. For instance, mean area under the curve square of GCN model the most performant model, and LGCN model, the least performant model, is only 2%. And also here you can see the log of all the models combined, and these curves are almost overlapping. Also, it is worth noting that models with singular GCN perform observably worse than models with two GCNs. And the difference between graph autoencoder models and variational graph autoencoder based models is insignificant. However, variational models perform slightly worse. The cause of such an effect may be the nature of the specific dataset upon which these models were evaluated. So, experimental results lead to the conclusion that the amount of GCNs may be more significant in some cases than the difference between graph autoencoder and variational graph autoencoder architectures. By experimenting with the configuration of GCN layers, prediction performance may be further improved. For example, the other further improvements of the proposed approach can be implemented due to hybridization of graph, convolutional, variational, and other network components. Also, it is worth mentioning that this work was partially supported by Knowledge at the Tip of Your Fingers, Clinical Knowledge for Humanity, project funded from the European Union's Horizon 2020 Research and Innovation Program. Thank you for your attention.